This is a very brief lecture on X-ray powder diffraction for the benefit of Ugrow students. I'm Dr. Jonathan Price. Let's start our excursion with talking a little bit about the progenitors of X-ray diffraction in general. And they are the father-son team that are the Braggs. So this is the only father-son Nobel winners. They won it in 1915 in chemistry. Their work showed the consistent spacing between simple crystals, and the instrument that permitted them to do this was constructed by these individuals. And it's down there in the left corner. It's essentially a device that allows you to put crystals in an X-ray beam and then see where you can find the highest intensities of those. And yeah, it doesn't look very safe, but it was a groundbreaking tool that we've only improved on to this day. A useful construct for our purposes is the electromagnetic spectrum. The electromagnetic spectrum speaks to energies that are being radiated, like light. Well, light is really a shorthand for the entire electromagnetic spectrum, but mostly when we think about light, we're thinking about the small part of it that our eyes can perceive, the visible part of the spectrum. It's much bigger than that, of course, and goes from very long wavelengths to very short wavelengths. And although it's a continuum, we break it down by wavelength intervals into individual names, such as radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. As we go from left to right on this diagram, we are going to shorter wavelengths, and a wavelength, symbolized by the Greek letter lambda, is the distance between two troughs in the waveform. Energies increase as we go to shorter wavelengths. This is reflected in the frequency, which is tied to the wavelength through velocity, so we can show both frequency and wavelength on the same scale. Wavelengths are shown here in the unit of meters, which is approximately the distance from your sternum to your fingertips. And 1 would be at 10 to the 0 right here. But we can find longer electromagnetic wavelengths in radio waves out to 10 to the 4 meters, or 10 kilometers. We can also go to much shorter wavelengths, and by the time we're around 10 to the minus 10 meters, we're in the part of the spectrum known as X-rays. The equivalent units are shown here with subdivided units like millimeters and microns and nanometers and picometers. Also, some objects of the same scale are shown below, and we can use electromagnetic waves to interact with things of about the same scale. Crystal lattices fall here, pretty close to the X-ray field. And some of the relevant techniques that we use in science are shown below. Here's X-ray diffractometry, our subject for today. Waves are cool things because they're energies, and as energies, they can occupy the same space. And that gives them sort of special properties, if you will. Even the kind of waves you think of on top of the water can behave in ways that are unique and somewhat powerful. Let's imagine that we have a wave tank that we've constructed with a type of beater bar that's generating a waveform on the surface of the water of the tank. If we looked from above, what we'd see is the crests of the waves above as single straight lines making their way across the tank with time. The wavelength, of course, would be the distance between the two white lines on this diagram. When you install a small occlusion on either side that is bigger than the wavelength, we can expect the wave to encounter this occlusion and generate a shadow beyond it, so that no wave energy actually makes it to the sides, but instead we see it propagate in the center only. But something phenomenal happens when you get about the same scale as the wavelength itself with your opening. If your opening is about the same size as the wavelength, then when the wave enters the opening, it propagates a new wave, a semi-circular wave in this instance, and doesn't permit any shadowing. So no shadows are being produced at this point. This generation and propagation of a new wave is known as diffraction, and that's what's important for our technique. It was Thomas Young who demonstrated this using a monochromatic light source, perhaps a sodium lamp. What he did is he used his monochromatic light source and sent it through a series of slits, shown here in this diagram as two parallel slits. You just need two or more. They have to have a separation width, and that width happens to be known as D, or D spacing. Keep that in mind. The other parameters to the Young experiment is that he needed a way to detect the light, and that simply is just a screen that the light can fall on. The screen is separated from the diffraction slits by a distance L. So our monochromatic light source, monochromatic means single wavelength, or single lambda in our symbols, is being sent through this, and when it's sent through this, we see multiple lines on the screen, sort of fading out intensity with distance from the center. They are parallel lines, and it's not a sense of occlusion of the light source being through, but we're propagating new lines from this. Young demonstrated that the variables we need to be concerned with here are the wavelength of the radiation source, the light, the distance between the detector screen and whatever is doing the diffracting, and the spacing of the slits in the diffraction grating. What's going on in this experiment? Well, the incident beam, which we can sort of think of in the same way as we thought of our wave tank with parallel lines of a given wavelength, is hitting openings of about the same wavelength spacing. And at that point, it's generating these semicircular and two-dimensional waveforms at both openings. Waves also do another curious thing when they overlap one another. They experience positive interference or constructive interference, where the waveforms build on each other. That intersection produces a strong image on our screen or detector. In between, we don't really get any kind of strong image at all. And this happens for all of the intersections. So these constructive interference wavefronts, through diffraction, allow us to learn something about the properties of the system. If we don't know the distance between our diffractor and the screen, we could figure that out if we know the wavelength and if we know the D spacing. Or if we left any of the single variables blank and knew the other two, we could solve that as well. Let's replace our diffraction gradient of a couple of slits with maybe a grid, which would work the same way, except it would produce a series of dots. Now let's scale that down. What else could have sort of this grid-like pattern in nature? Well, it turns out the construct of crystals made up of individual atomic sites, organized in a repeating pattern, makes an excellent diffraction grating. And in doing so, we might be able to learn something about the spacing between the atomic sites within the crystal. So a crystal diffractometer, as first constructed by the Braggs, operates in this principle. And a energetic source of X-rays, essentially in a glorified light bulb, emits X-rays. They are focused towards a crystalline powder. They interact with the crystalline powder, and they're able to diffract X-rays towards a detector. The length between the crystals and the detector is known and set by the instrument maker. The wavelength is also known. In the laboratory at MSU, we use a copper tube which has a wavelength of 1.54 angstroms. That's our monochromatic source. So all that remains is figuring out distances in our diffraction gradient, or in other words, the crystals that we put into the instrument. The result is moving this through a series of angles called theta, with a detector moving along at 2 theta. The standard plot or pattern is a plot of the intensities of the X-rays received as we progress through the series of angles, using the detector's angle as this x-axis, 2 theta. The Braggs found this relationship, which is important for our work, that n, which is a coefficient that signifies the order, times wavelength, which we're using lambda, is equal to twice the diffraction distance, the d spacing, and the sine of theta, the angle at which the sample is going through. For our purposes, n is going to equal 1. The first order is what we're interested in, so it goes away, and we're left with lambda equals 2d sine theta. Let's talk a little bit about the source of the X-rays, the X-ray tube. As I said, it's kind of a glorified light bulb. What we're doing is applying an incredible amount of voltage to it. About 30 kilovolts of voltage in order to drive this system. We do that to a cathode on one side. It runs through a filament wire that generates a boatload of electrons that are propagated towards a anode down at the other end. The electrons then hit the anode. The anode can be made of various things, usually, should be made out of heavier elements. But in our case, it's made out of copper itself, which may also include the stem that holds the anode. We need a really pure material. We want to make sure that we only get one wavelength out of the tube as a process. Now, the electromagnetic radiation, which includes X-rays, is being generated in all directions. But we don't want it to come out in all directions. So the tube is constructed essentially to shield the radiation from leaving the tube in all directions except one. A thin window of beryllium is placed so that the X-rays see this as a transparent way out. The X-rays then leave through the window and then can be used for our operations. What we're doing in here is a process of generating X-rays as the movement of electrons. And now we need to talk a little bit about the fact that electromagnetic radiation can also be thought of as a particle, or photons. And that's nice because photons are kind of like children. We're going to get one at a time. Every time we move an electron from a higher orbital to a lower orbital, we get one photon out of that, of a corresponding energy for that movement. What I mean by this is that by sending those electrons in from our filament into the target, we're pushing some electrons in the copper around. We're pushing them from their homes in the lowest energy orbitals closest to the nuclei. That becomes a vacancy that then gets filled by a higher energy orbital electron. When it pops in, we release a photon. The energy is completely predictable and relatable to the changes in energy from the highest level of energy to the lowest level of energy, and can also be equated to the frequency of the photon's waveform when you multiply it by a universal constant known as the Planck's constant. Where's wavelength in all of this? Well, frequency is related to wavelength by the speed of light, and in this case we use the speed of light in a vacuum, c, divided by the wavelength. So our energy of our photon, or the X-ray of interest, is just going to be related to the wavelength through Planck's constant times the velocity of light in a vacuum divided by the wavelength. This is fluorescence. Fluorescence is the ability to generate, or the process of generating, light, electromagnetic radiations from electron jumps. X-rays are special. They go under special names as a consequence of it. But again, these are arbitrary because electromagnetic radiation is a continuum. It's continuous. There are no real dividing lines in it. But we do discriminate between high voltage and low voltage, and that's relative speaking, X-rays. Those at lower voltage, say a tenth of a kiloelectron volt to about 10 kiloelectron volts, are known as soft X-rays, and those above are known as hard X-rays. We'll be using hard X-rays for our equipment. By the way, an electron volt, it relates the amount of movement that we have for an electron when it's being propagated under a volt of potential. And of course, now we're talking about thousands of them when we talk about kiloelectron volts. It's just a unit of energy. And if you're more comfortable with joules, it's equivalent to 1.60218 times 10 to the minus 16 joules. Although maybe you're not comfortable with joules, perhaps you're more comfortable with the kilowatt hour, which is what the power company is using to disseminate your units of energy to your house. Well, that's equivalent to, it's 4.450 times 10 to the minus 23 kilowatt hours. This is a small amount of joules and an even tinier amount of kilowatt hours. We can, of course, talk about X-rays in terms of wavelengths as well. The wavelengths are decreasing as we go from left to right in opposition to the way the energies are increasing. And again, we sort of have this dividing line between longer wavelength and shorter wavelength X-rays, but they're all pretty short. We're also using a unit here called the angstrom. The angstrom is 10 to the minus 10 meters. And it's also known as a tenth of a nanometer because a nanometer is 10 to the minus 9 meters. Nanometers are more in fashion for publishing and talking about things in science, but we will use angstroms because of, well, convention and tradition. We still use the angstrom very much in X-ray generation and X-ray diffraction. So 1.2 angstroms is about the dividing line between longer wavelength and shorter wavelengths. 124 angstroms would be considered a long wavelength X-ray, and 0.1 or a tenth of an angstrom would be short wavelengths. This is about the scale of the size of atoms, an angstrom or more. So when we think about this, we're on the right size for dealing with the construction of atoms. Likewise, the detector angles increase as we're talking about increasing wavelength, shown here in 2 theta as a rough approximation. And of course, the operating equation for this is the Bragg equation, shown once again. Must be pretty important. Okay, one other important idea to understand is one of the reasons why we're operating at such high voltages. Turns out that you can get the tube to create all sorts of noisy radiation at lower voltages, as shown on this diagram to the left. But you have to be above certain voltages to get coherent radiation that we could actually use for diffraction. What we're counting on is a radiation peak of its own from our copper tube that happens with increasing voltage. That also shifts the background around as well. We're after this peak right here, known as K alpha. There will also be a corresponding K beta peak very close to that, and we can't really stop that, except we can fish it out of the signal. And we will do so in our instrument with a quartz crystal that does a little diffracting on its own in the way of detecting. Should be noted, and rhodium is shown here as an example, that there are other coherent radiations as well, including these L peaks out here. But they tend to be smaller and less useful than the K alpha radiation that we're after in generating X-rays. What's with all this nomenclature of Ks and alphas and Ls and betas? Well, that is a traditional way of talking about the radiation that's being generated. And despite the efforts of powerful organizations that try to get scientists to communicate in much more sensible ways, most of us still use this older notation system known as Sigma notation. What it comes down to is the individual photons that are being generated when an electron moves from a higher energy orbital to a lower energy orbital. And they have been given these traditional names. You might be aware that one way to talk about the energy positions of electrons is in terms of Barkla nomenclature. That is, these letters that start with K and then go to L and then M and to N and up. Barkla nomenclature also still is in fashion in the X-ray community, although a more appropriate way to talk about this is in terms of their initial quantum numbers, their position numbers, N. K would be equivalent to N equals 1, L is equivalent to N equals 2, and so forth. And these are physical distances away from the nucleus of an atom for the electron orbitals that are concerned. You might also be aware that electrons that are closest to the nucleus really don't have a lot of options in the kind of orbitals that they can occupy. That they've got to be pretty close to the nucleus, and they're limited to sort of a spherical geometry as a consequence of that. And there's only room for two in that single geometry. But when you get out further, you're permitted more distributions of electrons in their probabilities. And as a consequence of that, you have more options, if you will, and slightly different changes in energies to accommodate in order to send electrons towards the lowest K or N equals 1 orbital pathway. And that's true as we move further out the atom. Barium is shown here, number 56, because it is a fairly massive atom that can attract a large number of electrons, 56, to achieve neutrality. So the pathways are not only well known, but well traveled by the electrons that are involved. What is K alpha 1 radiation and K alpha 2 radiation, jointly known as K alpha on the previous screen? It is the movement of electrons from the L orbitals, L3 and L2 to be specific, down to the K, or 1s, 1 orbital that's at the bottom. It's this jump right here. So we call it K because we're ending up in K, and alpha denotes this jump, which turns out to be the most energetic jump you can do in these orbital structures. Beta is a jump from further out in the M orbital. So the beta jumps are M3 and M2 jumps into that. You might guess that L alpha and L beta correspond to jumps to the L orbital, and you're correct. There's also M peaks, but we won't worry about those. We're not even worried about the L peaks at this point. So the nomenclature here gives us some idea of where we're expecting the propagation of X-rays to generate from the electron jumps. We will see K alpha 1 and K alpha 2 on our data because we can't separate those two. But fortunately, they come very close together and won't cause any problem. And again, K beta tries to come along, but we fish it out of the signal. There are several types, well, really two primary types of diffractometers in their settings. This is one type here that has 2 moving arms on its goniometer. The instrument we have in our lab has 1 moving arm. Just the detector and the stage move. But both work the same way. What we really need to know is that angle of movement, right, theta, and we need to know the distances involved, and that's, of course, set up ahead of time. The pieces of the equipment are quite straightforward. We have an X-ray tube, like this one here. The only window open on this tube goes out through a series of slit boxes. Right here, collimator, shown as primary X-ray optics, down to wherever we're holding the sample that's going to travel around. And from the diffraction that we get on the sample, we send it through another slit box on its way to a detector. And this whole thing rotates, so we go through a series of angles. As we go through a series of angles, the X-rays encounter different plane geometries and are then diffracted through these different plane geometries. We're going to use a symbol system called Miller indices, which are 3 characters. These 3 characters tell us about the inclination of the planes involved. And in a typical powder grain, powder diffraction sample, we'll be able to see a lot of diffraction going on simultaneously. Every time we hit the angle, the particles in the powder are randomly distributed, which allows us to automatically see a lot of diffraction at the same time. So in powder diffraction, what we collect is called a diffraction pattern, and it looks something like this. So a diffraction pattern is presented typically as a series of 2 theta over the entire length of scanning. So in this instance, 5 to, looks like the data stop at about 92 theta. And what we're looking for are places where the Bragg equation is satisfied, where that theta, which is half of the 2 theta angle, is right to reconcile the wavelength we're using with the spaces that are in the lattice. So we can see that each of these intense peaks are high intensity of counts that tell us about which planes are generating this, at what spacing those planes have. And we can calculate that through the Bragg equation because we know the wavelength of the radiation and we know what we're talking about in terms of the angles that we have gone through. And I've shown the Miller indices here for 3 different spacings for this particular crystalline material, quartz, a very common crystalline material on the surface of the Earth. This is structural information. Quartz is made up of silicon and oxygen, and there are not a whole lot of things you can put together that have these same kind of spacings where you can anticipate these same kind of peaks. So it is more or less a fingerprint of quartz, but it doesn't particularly tell you that you've got silicon and oxygen together. It just tells you you have the right spacing to put together atoms of silicon and oxygen together in what we call a quartz crystal. This is useful because things that are made up of the exact same chemistry but put into structures that differ can be discriminated by X-ray powder diffraction. In mineralogy, we call these things polymorphs, which is shorthand for different structures, exact same chemical composition. And these are 2 examples here. Calcite is calcium, carbon, and oxygen put together, CaCO3, and it's probably the more common version of that. But aragonite is also a way to put calcium, carbon, and oxygen together, CaCO3. Note the difference in the peaks. The structures of these 2 are very different from one another. There's 2 good news things from this. One is that I can tell calcite from aragonite by paying attention to this pattern. And the second is that we could actually understand these structures that make up these two different crystals based on the appearance of the peaks. So two critical things that we get from every diffraction powder is one, the position of the peaks. In other words, where are they in 2 theta space? Because that's contingent on how big the structure of the atoms is put together. And then also, which are the big peaks and which are the small peaks? In other words, the relative intensity of the peaks is going to be important as well. I learned this technique very many years ago, but I learned on an old machine in its day. So don't judge the professor by the machine involved. This is some pictures I found on the web that are very similar to the machine I used back in the day. This was a Rigaku D Max B. Beautiful instrument. Very open and easy to use. This is lead shielded glass around it so you can see what's going on. Power controls are all manual. You had to be very careful with those. One thing that's bad for tubes is applying too much voltage without enough current simultaneously. And much like an old-fashioned light bulb, if you keep turning them on and off, you're going to wear them out. So exercising care. There's a red light to warn you that the X-rays are active. And this machine is actually on its side compared to a previous picture of what the goniometer looks like. The goniometer is actually horizontal here, and the sample would basically sit on one space, and then the detector would travel along on a horizontal plane. Very old computing system attached to this. Even at the time, it was kind of laughably old. This is pre-personal computing. This is called a mini mainframe put together by the DEC Corporation. And it used these funky 8-inch floppy disks that held virtually no information. And you had 2 ways to interface with the machine. One strictly for graphics, which actually looks more or less like the computers of today. But most of the instructions were put in on a teletype, which you would type in and it would print out on a piece of paper instead of a monitor. Because why wouldn't you want a record of what you're doing? All right, enough trips down memory lane for the instrument. We need to talk a little bit about the history of the data itself. X-ray powder diffraction actually works as an analytical technique because you can compare a crystal you found on the street with a database of already analyzed materials. And that database is a highly groomed and maintained set of files that, even before my time, were originally kept on index cards, roughly 3x5 index cards. As a consequence, they're still known as cards, even though nobody touches cards anymore. This is what an old traditional card would look like, and all the information that you would have on it. Some important things that we can pick out about this is that, of course, this was done using copper radiation, but the card doesn't necessarily assume that you're using the same tube. It does tell you the D-spacings involved and their intensities that you'd expect on a relative scale. In other words, for this particular card of NaCl, sodium chloride, halite is the mineral name, the strongest peak is this one with a spacing of 2.821 between the planes. And that corresponds to a Miller index number of 200. The star up in here is actually important for our purposes. Star cards are cards from data sets that have been analyzed over and over and over again. So the original reference material has been done by a number of labs. They keep coming up with numbers, they average them together, and we're convinced that this is as good as it's going to get. Star cards are primo. If you got a star card, that's a good sign. We'll see this in our data set, even though our data set, our database that we're using, is completely on the computer. In other words, we'll reference the data set without picking cards out from a filing cabinet. Instead, we'll let the computer search through it and say, oh, I found things that have matched. And by finding those matches, we'll be able to see what's going on. So, this has been a brief overview about X-ray diffractometry. Enough to be dangerous, but we'll really want to spend time on the instrument to understand it better. What we need to know about the physics of this is that electromagnetic waves, specifically X-rays, can be used in this case, but like all waves, can diffract through openings at a scale of the wavelength. Because X-rays are so darn tiny, we can send them through the spacings that are between the atomic structure of the crystalline materials. And they've got to be atomic structures with organization, and crystals have got that. So X-rays of that size that will diffract through an atomic lattice follow Bragg's law, which, again, is a coefficient which we'll largely ignore and treat as 1, so it just goes away. The wavelength, lambda, equals twice the d spacing, that is the space between the atomic planes in our sample, and the angles involved. We'll take the sine of that to find out where we are. Diffraction occurs at specific angles for lattice spacings. We can match that against a database to reveal mineral identities, and we can learn something about the construction of the minerals by the way the peaks present themselves. And that is it. We now understand the basics of X-ray powder diffraction, and we'll be able to use it to understand the crystalline materials we're interested in. Thank you for listening.